very weird. No, yeah, so this is not normal.
Right. So the next presentation will be presented by Professor Carolina Honkala from University of Jyväskylä. So the floor is yours. You have the pointer.
Pointer is there out of USB ports. So you can slide. Can just turn them off. Yeah, sorry.
As long as I have my slides, I'm not that skilled as Annette to speak this without slides. Yes, like Annette mentioned, that our role is then to try to model the active site, which, as you probably understood, even without her being able to show the slides, that this is super complex task. So, and this is not the first time people try to do it. And okay, I skip this for the sake of the time, only point out that last year I had a very nice PhD student who was kind of part-time artist, and he made beautiful pictures for his thesis, which I now borrowed. So how to model the active site for CO2 hydrogenation to methanol via DFT or any other methods, that we need to build a structure model for, not for the entire catalyst, but for the active site. Of course, if we know from experiments what is the active site, then it's much easier task for us. But if you don't know, and if the catalyst is dynamically changing during the reaction conditions, as in this case, as Annette explained, the challenge is much larger for us. And what we need to think about is that, okay, it's a multi-component catalyst system. It has metals, oxides, promoters, you name it. And which part do we include into our model? Can we include all of it, or how do we limit the phase space to search for the active site? We need to consider that this catalyst is dynamically changing. Of course, with the density functional theory calculations, it's not possible to follow these changes. And then when we look at the reaction itself, we need to consider the different reaction pathways. This so-called formate pathway, which is dominating, as Annette said, but also the competitive reverse water gas shift reaction, which might lead to methanol or might lead to the CO. And in addition to this, we could have steps, vacancies, grain boundaries, amorphous regions, and what shall we do with all this mess? And what we have done in the past, in another project, we look at the zirconia supported copper zinc oxide systems, and there we make very naive models, but we look at the interfaces. We used highly idealized models, as everybody typically uses. So the standard approach from the computational chemist is that you discuss with your experimental friends, and then together you use a chemical intuition and you build the atomistic model, and then you use it. And if your results do not match with the experiments, you build another model. And yeah, quite often they match very nicely, but of course there are certain challenges. And but then copper zinc oxide alumina catalyst, and it mentioned these reactions, this main reaction forming the methanol, it's exothermic, and then the side reaction, the reverse water gas shift reaction is endothermic, and what implications it has to the reaction conditions. And this leads also for us, just to make on time, this we discussed. So question that what is the active site? And this cartoon here in the bottom shows how the catalyst changes during the reaction conditions. So you first have a copper deposited on the zinc oxide, and then you reduce it with the hydrogen, you get metallic copper zinc, and then you expose it to the CO2, you get this oxide, and then it continues. You might have a complete zinc oxide film, and then it might grow, and then you introduce all the reactants, you go back, you have some reaction, some bare copper sites, and this is a complete mess for the computational person. Okay. So do we have a reduced zinc oxide in the model? Do we need a metallic copper? Do we need copper plus ions? How about the alumina support? Do we need some aluminium atoms to our systems? And this has many different directions to which you can go. And then you have these two pathways. And as Annette said, we could have that we have one side that forms the methanol via this formate route, which is shown here green. And then we might have another side which forms CO and maybe in the best case also methanol via this road that is shown red. And but how these sites, how do they look like? And it says it's a zinc oxide copper interface, and that's our starting point in this project. And we need to build an atomistic level model. So we need to have some copper there. This we typically use as a metal slab. And then we have a zinc oxide. And in this project, what we do, we have been playing between a different kind of active site models. I will show them soon. And then we identify the active sites for the reactants. At that phase we are now. And then in the coming months, we will look at the reaction mechanism and study the thermodynamics and the kinetics for the reaction. And to compare directly with the experiments, we also aim at calculating these vibrational frequencies of the key intermediates, hopefully finding some kind of a match and to identify that we are operating with the same active site as our experimental colleagues in Fraunhofer Institute. So typically, these computational models, they have been highly idealized, like shown here on the right. You have a zinc oxide, perfect ideal nanorod on a copper surface, mimicking the interface between zinc oxide nanoparticle and the copper. Or you can have the vice versa model. Or people have also extensively used this kind of tiny zinc oxide cluster models on copper surfaces. And so the starting point is the experimental input and discussion with the colleagues. And then we have been building different models. I will show we have a graphitic model and then some non-periodic structures. And with this, we hope that we can really build an understanding for the active site. Because if the computational chemist does not have an understanding what's the active site, then the modeling becomes rather random. Graphic-like bilayer model. This has been presented in the literature. We are not the first one. And what we see, it's this kind of ideal two bilayer structure where the zinc oxide is fully covering the copper surface. We can, of course, introduce the vacancies. And we see that if we make the vacancy at the zinc oxide copper interface, it's more favorable. It requires less energy, around 60 kilojoules per mole, compared if the vacancy is generated on the surface of the vacancy. And these kind of different possibilities we can consider. And with this model, what we see is that if we have the ideal zinc oxide bilayer structure, the reactants only fusses on the surface, and the activation energy, for example, for CO2 hydrogenation towards formate is rather high. So it looks like this bilayer structure is not very reactive. And if we include vacancies, then we find that this bilayer, in the presence of the vacancy, is not very active towards H2 dissociation, while the hydrogenation of CO2 is more energetically favorable. But then the question is, how about under reaction conditions? Do we really have oxygen vacancies? And are there OH groups present? Because they can change the whole game. What we typically use, like I said earlier, we use the density functional theory method. Well, it's the most accurate method what people can use in the heterogeneous catalysis. But the problem is that the scaling with the system size is a limiting factor, so we can only look very small size systems. What we have employed in this project is also machine learning approaches to search for the structure motifs for active sites. And they're much fast. They give some structure motifs, which we can then test with the DSD. And well, in many cases, the accuracy, yeah, you need to be a bit careful. The accuracy can be okay, or it can be complete crap. So care must be taken. And the bonus is that with these machine learning approaches, you can look much bigger size, larger systems than with the native DSD calculation. And we employ now this machine learning approach to look non-ideal, non-highly symmetrical structures on the copper, hoping that we then identify different kind of active site motifs and then look at how their CO2 binds and activates on those sites and how is the reactivity. And this is the computational approach. We have some random initial structure where we start with, and we use machine learning accelerated genetic algorithm to search for the structure motifs. And once we have those structures, we then employ again a machine learning, but this time with the minima hopping to search for the potential sites for the reactants to bind. And once in the end, we have a set of machine learned structures, we apply the density functional theory calculations, which is now can be considered more accurate. Of course, this is always a controversial issue, how reliable are these DFT calculations, but anyway, to verify that what is the binding energy, for example, for the reactant. And here are some submonolayer structures that we have considered in the MEMCAT project. And here we don't have that much zinc oxide on the system, but now compared to those highly ideal and symmetrical cluster structures, these have been obtained from the machine learning approach. They form this kind of network, leaving lots of empty copper sites. And these provide different type of copper zinc oxide interfaces. So I need to stress again that we are not trying to model the exact catalyst structure as such. We're just trying to model the active site. And we are looking for different structure motifs for that. And therefore, we can say that we also consider that what is the coordination of zinc and oxygen atoms. And for different kind of zinc oxygen ratios, stoichiometric or then oxygen deficient structures. So these are these submonolayer structures which do not have a clear crystalline structure. What Annette tells us is that under the reaction, before going that, here are some binding energies that we considered that, okay, what we see is that on these submonolayer structures, the CO binding energy is around 70 kilojoules per mole. And when we tested the structure where we included also a copper into a zinc oxide, we noticed that the CO2 doesn't want to bind into this copper that is on the zinc oxide, but it preferably finds this zinc oxygen motif where it binds. And independent of what structure we have, the binding is about the same, 70 kilojoules per mole. But Annette pointed out to us that, okay, under reaction conditions, they see some crystalline structures. So we went for larger structures and this kind of periodic elongated zinc oxide nanostructures, but we varied the zinc oxygen ratio. Normally, people have so far mainly considered that you have this stoichiometric ratio, but we chose differently. And we sampled different zinc oxygen ratios using the machine learning accelerated genetic algorithm approach. And we then evaluated the stability of these structures using this kind of a atomistic thermodynamic approach. And here we see the blue line is where we have oxygen deficient conditions, and orange one is where we have oxygen rich conditions. And you see that when we are in oxygen deficient conditions, the minimum energy, so most stable structure, is where we have less oxygen than zinc, while under the oxygen rich conditions, it's this kind of a 1-to-1 ratio is preferred. And here are some structures for you to see. Oxygen deficient structure on the left, oxygen rich structure on the right. And what we noticed is that the oxygen deficient structure, the zinc oxide copper interface seems to have less oxygen than all the available oxygen are on top of the zinc oxide. And how do these structures then perform in terms of binding the CO2? Yes, both of them seem to work quite nice, around 60 kilojoules per mole, not much different for the others. And our next step is then to look at I think this brings me to the end. Yes, to look at the possibility of including these copper plus ions that Annette was mentioning, also including the aluminium dopants into the structure. But the main point is that we use these non-ideal structure motifs to search for the active site. And during the project, the aim is that we can match with her experimental findings. And yes, this brings me to the end. The calculations were done by Pumi and Timo, and we closely collaborate with Annette and Nino with this project. And the MEMCAT gives the money, and the National Computer Center gives us the extensive computer resources. So thank you for your attention.
Thank you for this great presentation. Is there anyone for a question? Please.
Thank you for the very interesting talk. I'm an outsider, so I don't really understand, but I have two questions. Question one, you're interested is about the active site. Is the bulk playing any role at all in the calculations later? And it's related to the second question. What about the gas dynamics? Because you are taking into account the molecules at the surface. What happens if you have flow? Can you also include this into your modeling?
First of all, the role of the bulk. Yeah, in a sense, yes, combined with the reaction conditions, you might have that the vacancies are moving there. In that sense, yes. Also there, if I consider the alumina support as a bulk, it might be providing some dopants. So, and also the copper nanoparticles might provide. So yes, but of course for the reactivity itself, no, but the bulk might be the source of or reservoir for something. And the second, regarding these reaction conditions, yes, for the mechanistic studies, you can consider this influence, but if this this flow of gases dynamically changes your catalyst model. Yeah, that's more challenging. This could be, and without knowing anything, it could be that maybe with some advanced machine learning approaches, this maybe, not maybe yet, but this could be direction to go and look into it, but definitely not with the basic DFT. No way, it's far too slow.
All right. Then we have a question on the chat also. If you have considered the formation of copper and zinc alloys as an active site.
Yes, this is what extensively has been considered in the literature, but what Annette tells us that no, it's not an alloy, and it's originally during the induction period, it's an alloy, but when you introduce the reactants, this alloy oxidizes so that you have copper and zinc oxide. So that was why we neglected it from the present study.
Okay.
But I think there is.
Please, short one, please.
It's an optimization problem.
Yeah.
Yeah. So what is the target function? Is what minimize?
I mean, here we use this Microsoft Mattersill machine learning potential to describe the interactions between the atoms. What we then do is this genetic algorithm to search for different kind of structures. So in the level of the accuracy of the machine learning, we look, of course, the minimum energy. That's what we are minimizing. But because we don't know how reliable this approach in the end is, we pull out these machine learned structures and dump them into the DFT and then check that, okay, how stable are this and compared to the idealized slab and considering the reaction conditions as post-DFT approach. Yes, it's a check.
So but the machine learning does quantum calculation?
No.
It's a mathematical.
Yeah. In this case, it describes the interactions between the potential, but it doesn't describe the electronic structure directly in the same way as the DFT.
It's amazing. It's similar to often.
I mean, these results, these energetics that I was showing, these are the DFT results. So so we use it only to make these structure motifs, because otherwise we would pull them out from our sleeves like, okay, now let's look at this. It's a good idea.
Step is that.
Yeah.
I suggest that we move on to the next presentation. So thank you, Caroline, again. So
like this and without having it in presentation mode, and then we go through the slides.
If that's
That works, yeah, let's try like this.
All right, please.
Now only the sound is not working, or?
Can you hear us, please? Let's see if someone responds.
The presentation. No, exactly.
Yes, they can hear. Okay, that's fine.
And they cannot see us because this is disconnected.
Okay, but the video is fine.
It's
as long
okay.
as they can hear, it's fine. Okay.
Yes.
Okay. No, it's not fine.
Now you have to click it through here.
Okay.
And you can
Yeah.
use the pointer, the laser.
But it's you need to connect it. No, I would leave it.
Okay.
Okay. So we can, I would like only to briefly introduce the Plataforma Solar of Almeria, but we can skip this. And we are involved in the work packages in the Confetti project. And here we can see an overview. And the main proposal is from one side for the innovative and self-sufficient technology to capture carbon dioxide and nitrogen compounds for producing fertilizer, and the one in which we are involved, that is the recovery back of these nitrogen compounds by transforming into the fertilizer. And so here are the partners involved in this part of the project. Here we can see briefly our work is based on taking this nitrate contaminated groundwater that is highly recognized that the excessive use of fertilizer leads to high nitrate concentration both in soil and water. And so we would like to take this nitrate contaminated groundwater, treated them by solar driven photocatalysis to generate ammonium that could be used back as fertilizer for the soil. And so from one side we have the groundwater remediation, and from the other we have the valorization in a circular point of view. Okay, here there were a lot of animation to understand more or less the sunlight-driven process. So we have a photocatalyst that is irradiated by a source of light, that in our case is natural solar radiation. There is the generation of the couple electron hole. The electron and hole migrates in the surface and are able to reduce and oxidize the water. And in parallel, this electron, in the presence of nitrate species, can also reduce this nitrate into, through different steps, into ammonium. What is very important are the anoxic conditions, because the presence of oxygen could react predominantly with the electron to generate back water. So the main objective of this work was the selection of the most suited photocatalyst from one side, to tuning the operating condition to have an efficient conversion of nitrate into ammonia, and finally to assess the feasibility of the process in a real complex matrix, such as well water with different competing species. Here we can see the material and method. So we start with a concentration of nitrate between 5 and 125 milligram per liter. Two photocatalysts were used at initial concentration of 100 milligram per liter. All the experiments were performed in the presence of glycerol to enhance the process efficiency by capturing the oil. Different water masses were assessed. All the experiments were carried out under natural solar radiation, monitoring the solar UV radiance to calculate the accumulative energy for comparison purposes. As I said before, it's important to have the anoxic condition that were obtained by purging with nitrogen. And here we can see the photoreactor that in which through the hermetic tank the anoxic condition were obtained, and experiments were carried out under natural solar radiation in a compound parabolic collector reactor at pilot class scale with 25 liters of total volume, and of these 14 illuminated with an area of 2 square meters. And during the experiment, the nitrogen species, nitrate, nitrite, ammonium were monitored through ionic chromatography. The total nitrogen and the dissolved organic carbon through TOC analyzer, and hydrogen and carbon dioxide were also monitored through the microgas chromatography coupled with thermoconductivity detector. Here we can see the physical chemical characterization of the two well water that have been studied, and we can see that the well water 2 is more complex than the well water 1, with a higher concentration of all inorganic and organic species, and there is a natural occurring nitrate concentration that is higher in the second case, and all of them were spiked to achieve the 40 milligram per liter of nitrate for comparison purposes. That is a value that range between the average level of nitrates that are found in groundwater and the maximum limit that is admitted. So here we can see the optimization of the glycerol concentration in a simple water matrix that was the mineralized water. And so we can see that there is no significant effect of increasing the glycerol concentration. So we decided to use the lower one of 0.01. And in this case, we can see that we have nitrite accumulation with the lower concentration, so it's necessary to prolong over 2 days the experiments. And we can see here that the ammonium concentration reach a steady state, obtaining around 9 milligrams per liter of ammonium after 2 days out of the 35 that are the stoichiometrically one. Also, the nitrate concentration was evaluated, and we can see that there is an effect of the substrate initial concentration on the efficiency of the process. And as I said before, the experiment were carried out at 40 milligrams per liter because it's a real concentration that is generally present in the groundwater. As I said before, we obtain a steady state level of ammonium, and if we follow more the experiment, there was no more generation of ammonium. And so we can see that we cannot close the nitrogen balance. And if we compare the total nitrogen calculated as sum of nitrate, and ammonium with an organic carbon, we can see that this value is decreasing compared to the total nitrogen that are the species that are in liquid phase. And so we can see that there is a generation of another species from nitrate and nitrite that we cannot quantify. So this is one that does not allow us to close the balance. And we can see that there is also a decrease of the total nitrogen that starts from 27 milligrams per liter until 24 milligrams per liter, and this is due to for the formation of volatile species. So from one side, the formation of volatile species, and from the other, of a liquid species that we cannot quantify, is the sum of these allow us to close the nitrogen balance. Then, under the optimized condition that are 40 milligrams per liter, 100 milligrams per liter of catalyst, and 0.01 molar of glycerol, we assess the feasibility of this process in the 2 groundwaters. And so we can see that there is an effect of the competing species on the efficiency of the process. And so we obtain better results in the mineralized water than in well water 1, that was the simpler one, and then well water 2. And in the most complex water, we can see that we obtain a lower ammonium production, and this is due to the accumulation of nitrite. So it's important to increase again the glycerol concentration to have all the nitrate reduced to ammonium. And so we performed the experiment increasing 7.5 times the glycerol concentration. And we can see here by comparing, there was an enhancement for nitrate conversion. If we compare, this one is with the lower concentration of glycerol, this one is the higher concentration of glycerol. So we enhance the nitrate production and its degradation, and we have higher production of ammonium with 80% of selectivity of the process. We test also another photocatalyst. We can see that this was has a lower efficiency compared to the previous one, but in this case we have a lower water matrix effect, and similar results have been obtained in well water 1 compared to the mineralized water. And for well water 2, we have again the nitrate accumulation. And so also in this case, we enhance the photoreduction of the nitrate by increasing the glycerol concentration. And so just to conclude, we can see that the sunlight-driven photocatalytic reduction was successfully performed in a 25-liter compound parabolic collector reactor at pilot plant scale under natural solar radiation. In the presence of 40 milligrams per liter of nitrate, that was the optimal condition, we can observe that after 2 hours in the mineralized water, there was the formation of 9 milligrams per liter of ammonium. It was not possible to close the cycle, and the reaction kinetic was lowered by increasing the matrix complex, the water matrix complexity, because there are absorbing species that can be absorbed on catalyst site and can react with the reactive species. There was a problem of nitrate accumulation that reduced the selectivity, but increasing the glycerol concentration, we can achieve good results in terms of ammonium production. And so this process in general could be considered a great strategy for groundwater pollution remediation, especially in the centralized system under natural solar radiation as a renewable source of energy, and for the in situ production of fertilizer that can be directly applied for crop irrigation. And thank you for the attention.
All right, thank you, Ilaria. So is there any question in the audience? Yes, please.
Hi, thank you very much for your talk, very interesting. I have a curiosity. If you substitute nitrate by ammonium, what are the counterions? Because you cannot do this reaction. You substitute an anion by a cation in water. This is not possible. So what's the role of the counterions?
But finally, we are reducing the nitrate into the ammonium, and then on the other end, in the photocatalyst system, we are doing an oxidation reduction.
No, because you are going from neutral glycerol to CO2, so you don't have charges. So if you have nitrate and you pass to ammonium, you need something that you need. The solution must be neutral. So if you substitute an anion by a cation, what else is going on?
Maybe because we are also the hydrogen of the water are reacting, but they are generating hydrogen. And
That's reaction also. That's instead of ammonium. This is not outside reaction. Is that I don't understand it so that.
And from the part of glycerol, we are oxidizing and generating in the middle carboxylic acid.
That's not here.
It's a good point.
The overall reaction. You cannot have a reaction only with iron. You need neutrality in your solution. So what else going on?
It's a good point. I will think about.
I mean, it works. So I'm not totally to question your process. I'm just trying to think if you know what I meant. If you change the charge of your species, you should change some other species in the solution.
And you need to compensate, yeah.
You need to compensate that reaction. So maybe if you look at the whole real reaction, maybe you can get also some ideas of why the products are some kind, the nitrogen is missing or this kind of stuff.
Okay, I will think about what point.
Very interesting.
Any other question? And then I have one. Can you? Because I read that you said that photocatalyst 1. So is there anything that you can say on the type of photocatalyst that you're using?
Because we are going to patent the system, so we have to.
Yeah, that's fine. Okay. And then considering the design of the photoreactor, is there something special on the design of the photoreactor, or can you say how it works?
It's important that there are 2 parts. It's a biphasic system in which we can have the purging of with the nitrogen to achieve the anosine condition, and so it should be hermetic. No oxygen needs to enter because this will lower totally the reaction. And then there is a part of the liquid phase pass from the dark to the sunlight through a pump, and then we can analyze also the gas phase with the gas that are formed through gas chromatography online okay. With a micro gas chromatography, and so we can have in parallel what happened in both liquid and gas phases.
Okay, thank you. All right, so if there are no more questions, then let's thank again the presenter.
Thank you.